Thanks, Sriram. So Pramod ended with mentioning who he worked with. I should start with mentioning who I worked with. In particular, this is basically an abbreviated version of the thesis defense talk of my student, Sheng Tsai. Mayank Bakshi, who just started as faculty, research faculty in Hong Kong, and my colleague Minghua, all at the Chinese University. I'll be talking about I'll be talking about a bunch of different sparse recovery problems, but really maybe the take-home message is that there's a bunch of similar ideas that work in a variety of such problems. I'll try to highlight what they are. Actually, many of these are very similar to stuff that Kannan and his group have been doing at Berkeley. It sort of started happening in parallel, and then a little bit of a friendly competition, right, in terms of who comes up with algorithms for different things first. But the design philosophy that both of us, and in fact others also use, is similar, so I'll try to highlight that. All right, and as always, thanks to CUHK for supporting me, and in particular the Institute of Network Coding, and in particular my group, those of you who were here on Monday. This is Codes, Algorithms, Networks, Design and Optimization for Information Theory. At this point, I would normally take this off, and there'd be the group T-shirt below, except it's dirty, so I can't really wear it today. But yeah. All right. So sparse recovery. Now, in the literature, sometimes sparse recovery has come to mean just compressive sensing, and certainly that's one type of sparse recovery problem, and I'll talk about it. But I'll try to convince you that similar approaches could work in a variety of different estimation problems where you want to estimate a signal that is sparse. It's in a huge dimensional space, but the ambient dimension is huge, but the actual somehow signal content is concentrated in some sparse subset. And you have some measurement process. It could be linear or nonlinear, and I'll describe what each of these four different measurement processes and problems are. So compressive sensing, one way of motivating it is, one of many different ways of motivating it is, you have a base station, a bunch of different cell phones are talking to it, they're getting some noisy versions of it. The base station can really only hear things that are close to it. So how does it try to reconstruct what people are saying, right? And the way of thinking about this is, of all possible cell phones that are potentially speaking different things, the base station is going to get some linear combination of those things. Of all possible n cell phones, only k are sort of close enough for the base station to hear them. And from this measurement process, like of the n people who are potentially speaking in just m time slots, you want to reconstruct what each of them was saying. Since different cell phones are different distances away, and some of them could be speaking at the same point in time, so you could get linear superpositions. So in general, there's some linear combination of, which was in the previous slide, there's some linear combination of what people are saying, which represents what you're getting, right? And from these linear combinations, you want to reconstruct X. So if you know the sort of channel transitions, if you know what the relationship is between the inputs and the outputs, you want to reconstruct the vector. In particular, this makes sense if you have far fewer time slots than the number of cell phones, right? You want to reconstruct that, but of course it has to be at least as many as the number of cell phones you want to reconstruct, right? This is one motivation. And in particular, sometimes you have noise and you have approximate sparsity. So sometimes you want to reconstruct your X vector, even though there's some noise in the measurements, there's some E added to it near the end. And there's approximate sparsity, so the cell phones which are far away are also giving a little bit of interference, right? So that's maybe a more general sparse recovery setting. And in particular, in the next few models, I'll even relax the requirement that A has to be linear. Sometimes your measurement process is inherently nonlinear. I'll describe a couple of such measurement processes as well. Okay, but the goal is going to be similar. X is lying in a high dimensional ambient space, but its actual signal content is concentrated within some k, which is much less than n number of indices, number of coordinates. You want to reconstruct X, knowing A, which is some linear or nonlinear measurement process, and knowing Y, in the presence of potential approximate sparsity and noise. Okay. To simplify things, I'll be talking about, in this talk, I'll ignore the effects of noise and approximate sparsity, but these can be handled via some somewhat standard techniques. All right, so just to get a sense of things, what's the network tomography problem? So there's a network, you know what the topology is like, but there are some bottleneck links. You want to estimate which links are bottleneck links. What you get to measure are end-to-end measurements. You get to measure, you put in a packet at one side of the network, you get to measure the end-to-end path delays. And from these end-to-end measurements, you want to figure out, well, what are the link-wise path delays? Hopefully, very few of them are actually delayed. So these are sort of linear measurements, but the restricted linear measurements. You can only take measurements based on the network topology, right? And this introduces its own set of challenges. Here's a third model, compressive phase retrieval. So here you have nonlinear measurements. So here, maybe you're getting the intensity measurements of something which is, so you have some underlying real signal. So maybe that corresponds to someone's face, and you also want to figure out the distance of each pixel on the face from the camera, lens. So somehow there's the intensity that corresponds to the amplitude of the light coming from you. But it's also the phase. The phase corresponds to how far away that particular pixel on the face is from the lens, right? So I like to joke, this is like face recovery from phase recovery. That's one way of thinking about it. And here you just get to measure the intensities. And I'll talk a little bit more about algorithms for that. Finally, there's the group testing problem. Again, it's a nonlinear problem, and again, many of you probably already know what it is. I'll just do a quick overview. So there's a bunch of people. Some of them have a disease. You want to figure out who has the disease. So there are n people. K of them have a disease. But instead of testing them individually, you test pools of them, you test groups of them. These tests are disjunctive measurements. These are like OR measurements. So you mix the blood from different people together, and the goal is to try to figure out who has the disease with the minimum number of tests, right? And again, you could have noise sometimes, various things could happen. But notice these tests are nonlinear, right? Because if even one person in the pool you're testing has the disease, then you'll get a positive test outcome, otherwise you'll get a negative test outcome. So here you have, again, inherently nonlinear measurements. You want to reconstruct the signal from these things. All right. So 4 different models, but my claim is that somehow similar underlying ideas work. So my goal is going to be just to explain the intuition for the linear model without too many details, and then show how for one of the nonlinear models, for phase recovery, how you have to tweak. So the same idea doesn't work exactly in each of the models. You have to tweak. But how do you tweak? And I'll give you one of those examples. Okay. All right. So let's start with this compressive sensing. And here's this particular, the idea for this slide we stole from Samir Pawar's slides, Kannan students. Really nice way of explaining things. So the idea is, well, let's say there's 5 guardians who are trying to guard some gold bars. One of them is actually, he's actually, instead of being a guardian, he's stealing some gold from his gold bars. So he steals an unknown amount of gold from each bar under his control, and you want to figure out who it is. Which one is it? How much is he stealing? So with the minimum number of weighings, so each of them should be 100 grams. So because you can weigh them, you can figure out that it should be 100 grams. So one way of doing this is to measure like the total amount of is to measure the total amount of weight. If you take 1 from each stack, you figure out it's 490. So that tells you, okay, what he's stealing should be roughly 10 grams, right? And that's like taking a linear measurement of this form. You're just taking the summation of xi's with coefficients which are 1, and you figure out that it's like minus 10. And then I'm sure many of you have seen something like this before. Then you take an unequal number. You take different numbers of gold bars from each stack, and then you get some linear measurement, which looks kind of like this. You figure out it's in this measurement it's minus 40. So it must have been the case that the 4th stack was actually the bad guy, right? Because the ratio of the total weight in this second measurement to the first measurement was 4, so it must have been this guy, right? So notice, even though, like in principle, this measurement is measuring a large number of people, it's measuring n people. Like a single measurement enables you to figure out which guy it must have been. It's like this bad guy has left a signature, which with a small number of measurements, with 2 measurements. The first measurement to figure out what the difference must have been, and the second measurement to sort of normalize it. You can figure out which guy it must have been, right? And this is, in some sense, the takeaway message of this thing. So this quick reconstruction can happen because our measurements are somehow structured. So if there's some structure to the measurements, and here I've given an example with a very carefully chosen structure, right, just to make it obvious. But if there's some structure to the measurements, often not only do you get information theoretically optimal recovery, but you also get very fast information theoretically optimal time complexity also in recovery. And let me repeat that in, I think, an upcoming slide, well, a couple of slides down the line. So, well, okay, I'll repeat it later. One more idea, so a second version of the gold bar puzzle. Suppose there's two different thieves, what do you do? So suppose by magic, suppose you know that this is a bad group. So what's a bad group? A bad group is one which has too many thieves. Yeah, you don't really have any hope of figuring something out. And suppose by magic, you know that something is a good group. It has at most one thief in it. So then you can somehow iteratively use the same process. You can you can try looking at the bad group. You can look at these structured measurements. The ratio will give you something that's not an integer. So this tells you, okay, this group is bad. It has too many bad guys. So maybe let's not start with this group. Let's instead start with a good group. So this group happens to give you a ratio which happens to be an integer. So maybe it's a good group. Maybe it has just one bad guy in it. So now that you've figured out that this is a bad guy, so now you figure out who the bad guy it is. You then do some cancellation, because after all these measurements are linear, right? And then the ratios in the previous group, which is a bad group, now becomes a good group, and then you can figure out who the bad guy is in the previously bad, now good group, right? So this process should be familiar to many of you. This is basically just a peeling process, and you know, this shows up all the time in coding theory. So this second idea is just sort of linear cancellations. And in the linear setting, two of the problems I mentioned are linear. This works out. You can do linear cancellations. It gets trickier in the nonlinear setting. You have to. That's where usually most of the tweaking needs to be done. You need to figure out how to mimic such a linear process, even though you have nonlinear measurements. And you know, some finesse is needed over there. Okay. All right. So that's basically that's one of the major themes of this talk. You can represent each of these things by some bipartite graph, and if you have a singleton, that's like the good group. Again, we've stolen notation gleefully from Kannan's group. So if you have a singleton measurement corresponds to a group that you're measuring, which happens to have just one good guy. Then using that gold bar puzzle idea, you can figure out who the bad guy in this group must have been, who the non-zero component, that's in this case that's x3, must have been in this measurement. And then once you figure that out, then you can do some cancellation. You can figure out, you can cancel the effect of that thing out, pass the message back to the other side. And then what was originally a multiton, what was originally a bad guy, what was originally a measurement which had more than one non-zeros can be cancelled out. It becomes a singleton, and then you can decode. So basically this comes down to trying to prove two things. So you want to prove that there are good bipartite graphs, there are these good measurement processes where you have these output measurements on the right hand side, the inputs on the left hand side, and you have these good measurement processes where at least a significant fraction of the measurements are singletons to begin with, because these singletons somehow allow you to bootstrap the process. You start off with a green node, you start off with a node which has got just one bad guy in it, one non-zero component in it. Then you figure out what the component must have been, the value, then you cancel, and so on, right? So first of all, you need to guarantee that there are some such good graphs. This again is somewhat standard from techniques in coding theory, codes over graphs. So one type of analysis tends to be along the lines of I'm jumping ahead quite a lot. Tends to be along the lines of looking at expansion properties of graphs or other techniques, which I guess I'll mention briefly later. But really, again, the key message that I maybe want to get across, which is slightly less appreciated, though again some people, including Kannan's group, have looked at it, that instead of just choosing bipartite, instead of just stopping at the point at which you choose the bipartite graphs, if you also figure out, like once you have the corresponding bipartite graph, what values to put over there. Instead of just putting zeros and ones, if you put values on the non-zero components carefully, that those choices of values you put over there also have a role to play. They don't necessarily have a role to play in terms of minimizing the number of measurements quite as much as they do in terms of minimizing the amount of time required to reconstruct. So if you care about computational complexity as well as sample complexity, then choosing these measurement matrices somewhat carefully helps. And actually, one can also argue that in some settings, these measurement ensembles actually happen naturally. The cell phone example I gave, I claim, and I can talk more about it if you're interested, but I claim that cell phone example, for example, naturally fits in the ensemble of matrices that you'd like over here. Okay? This is all very sort of hand-wavy, philosophical. I hope to give just a couple of concrete examples. I have around 10 minutes, so I'll maybe look at the phase retrieval part. So our contribution, again, is not just in minimizing the number of measurements, but also in minimizing the decoding complexity. And as an example of the type of algorithm that you can guarantee here, so it's sort of clear that if you have a k-sparse signal out of something that's sitting in ambient dimension n, you can't hope for less than k measurements, less than order k time, because after all, just writing out the input itself will take order k time, right? And there's a bunch of previous work which is, it tries to optimize the decoding complexity or the measurement complexity, but if you do this, you can basically hit both, almost bang on, up to small constant factors, like constant factors which you can explicitly calculate, which are of the order of 2 or thereabouts for the number of measurements, or up to 15 or so for in terms of the decoding complexity. So literally, really quite spectacular. Yeah. All right, so that's what happened. And again, just to highlight, this parallel work by Kanan's group, which is really quite nice. They did optimize the measurement. So we had order optimal results. They actually optimized the constants and have some really nice results. Okay, so that's for compressive sensing. And in the interest of time, I think people have already gotten a flavor of what's happening. So there's some expansion properties which allow you to prove the existence of good graphs. I'm going to skip over that. I'm going to skip over what that peeling process really is. Like, we choose to do it via complex matrices. There are other ways of doing it. There are reasons to use complex matrices. I'm going to skip over all of that. Just to give a sense of something, I'll try to talk about the compressive phase retrieval. This is the nonlinear part, right? So again, you have a signal. It's sparse. So your x has just k out of n non-zero components. You want to figure out what it is. But what you get are not quite linear measurements. You get intensity measurements. So you get the absolute value of the summations of ai, xi, something like this, right? And again, think of this as just your photon detector can only count the number of photons coming in. It can't figure out the phase, maybe. Okay. So from these amplitude measurements, you want to figure out the original signal. And part of the challenge is, well, if you think about it, you can't really hope to reconstruct the signal exactly. Like, for example, suppose before you took the intensity, before you took the amplitude, your a times x, the linear measurement of a times x was something like 2 times e to the iota pi by 3. Then, once you look at the intensity, then you'll get a 2 at the output, right? But even if this was, multiplied by 2 to the iota theta by 2, even if you multiplied the whole thing by, you rotated the phase of the whole signal by e to the iota theta, you would still get 2 at the output over there, right? So at least up to a global phase, you can't hope to reconstruct the signal. But so again, if you have some signal, you could rotate the whole signal by e to the iota theta, you would still get the same output. So up to a global phase, you can't hope to do better than that. But indeed, it turns out you can reconstruct the signal up to a single global phase, up to a single e to the iota theta. It's non-trivial to figure out what's the minimum number of measurements required to do this. We don't try to get the information theoretically optimal number of measurements, but we get up to a small constant factor of it. Okay. So in this case, again, you can try using a similar idea. You can try figuring out singletons. So you can try to take measurements so that you can figure out the intensities of various things, right? So you have that. But then the problem is the cancellation doesn't quite work, because now you're getting absolute values of intensities, right? So you can't quite cancel things out. So you have to be careful here, right? And so peeling is not allowed because you can't. You just get absolute value of x1, absolute value of x2, but taking the difference of these two is hard. And you also want to figure out not just the magnitude, you want to figure out the phases. So here's a simple little idea, which is basically, so suppose someone gives you the magnitude of x1, magnitude of x2, and magnitude of x1 plus x2, for example, or some linear combination of them. Then by the triangular inequality, you can by basic trigonometry, you can figure out it must have been like this, or actually there's some degeneracy. It could have been the flipped version. So if you know the magnitudes of two different numbers and some linear combination of them, you almost know what the angles between them must be. So if you just take one more measurement, let's say x1 plus iota x2 and so on, then you can figure it out exactly. You can figure out it must have been the one on the left hand side. Okay, in this case. So basically the idea here is, well, with some extra number of measurements, you can take care of this degeneracy. You can try to figure things out. So what does this mean? It means that if you have measurements which have something like this sigma structure over here. So what's a sigma structure? So let's say you have a measurement, you have a singleton, you have a measurement where the corresponding non-zero node being measured is only x1. Like it could have other nodes being measured, but all of those have zero magnitude. So only one non-zero node is being measured in this y1. Only one non-zero node is being measured in y2, and there's a doubleton, there's a node in the middle which is measuring both of these non-zero nodes. So in this scenario, in this sigma structure sort of way, you can hope to reconstruct both of the x1s and the x2s, right? Because this will give you the magnitude of x1, this will give you the magnitude of x2, and this could give you some linear combinations of the magnitudes of x1 and x2, right? So the trick then comes down to figuring out, well, what sort of graphical structures have a decent number of sigma structures, right? And that's really where it comes, like what you have to analyze. So over here, like. So some of these slides are because of my student, and my group, we like our wiggly animations, and I've lost track of which things wiggle now. Oh, that's right. So this thing is wiggling, right? This is a sigma structure. Okay, there we go. So this is a sigma structure. You can decode using this one, and now you have something like a multiton. So in this case, this y3 is a linear combination of x2, x4, x6, all of which are non-zero. So right now, this is not necessarily that useful to help us decode, right? So at this point, we could really call it a useless node. So certain, like a basic, you can calculate the expectation that you'll have singletons, you'll have doubletons, you can calculate expectations of sigma structures and so on, and things work out in expectation, and all of that works out. You need some nifty algebra to make sure that you can do cancellations carefully. It turns out, if you very carefully choose your measurements, then you can solve quadratic equations and try to figure out what the corresponding non-zero components must be like. I'm getting close to my time, so I'm rushing through things. Let me just say, much of this is algebra. Like the basic message I want to get across is the linear peeling process is hard to do, but you can replicate that by carefully choosing your measurements. Again, the message to take away here is you want to choose your measurement ensemble so that given the specific nonlinearity of the problem, you can try to undo that nonlinearity and be able to peel and so on. So with a bunch of different tricks and suitably choosing your ensemble, it turns out that you can then patch together. So once you know the relative phase between x1, x2, between x2 and x3, and so on, then you can figure out, as long as you have a connected graph, as long as you have enough of these sigma structures, you can figure out what the relative phases of each of the non-zero components must be with respect to each other. And by carefully optimizing the degree distribution and so on, you can get it down to order k measurements, order k log k decoding complexity. Again, this happened to be also a problem that Kanan's group and his students also looked at, and there's some nice work there. I'm not going to go over the degree distribution optimization. Let's not worry about it. 1 minute, and I'm basically giving my final sort of take-home message, which is. So even here you can get order k complexity, order k number of measurements, nearly order k complexity, not quite that. And even for the group testing problem, depending on which version you're looking at, it's close to order k, the information theoretically optimal number of measurements and decoding complexity. I'm not going to go into the details. But the take-home message is you want a good bipartite graph. These things have been examined fairly well in the coding theory literature. But when you choose the structure, you choose the non-zero components, you decide what to put in them and somewhat carefully, then in that case, your decoding complexity can drastically be sped up, right? And yeah, these singletons, multitons help a lot. I'm done.
Thank you very much, Sid. We'll take a question while Aaron's sets up. Any questions?
Yeah, I have one. So there must be some generalization of what you're trying to infrastructure to 3 things at a time and even more things at a time, right?
Indeed. So, but because it's non-linear, so if for these phase recovery problems you have to do these cancellations, then you have to do it carefully. For phase recovery, it turns out you can do it. For depending on the type of non-linearity, for group testing, more challenging. So, problem dependent. Thank you, Karan.